Hi everyone, we're going to start in lesson 2.4, but we're just doing the ending of 2.4 today. Hopefully we got through examples 1 through 4 in class sufficiently, and now we're going to continue section 2.4. This is a longer section, so we're going to do some of this at home. What I want you to do first is pause this video and read on page 97 the upper and lower bound test. It's the box in the middle of the page. So go ahead, read over that, and you can pause this video now. Okay, hopefully that you got to read that, and that may have felt like a lot of words, but we're going to simplify it. We're going to apply these tests, so the upper and lower bound test, to example 5. In example 5, it says that we want to show that any real, let me get my highlighter, we want to show that any real zero of p of x lie within the interval -1 to 2. So in this interval, we can see that -1 is the lower bound and -2 is the upper bound, okay? So that's our interval that we're looking in, and we want to apply these upper and lower bound tests to show that any real zero that is a root of p of x lies in this interval. So the first thing that we're going to do is test, is 2 an upper bound of the zeros or roots? So meaning, is there no zero that is greater than 2? So for p of x, we've got p of x up here, right? For p of x, if we look at all the zeros, they exist, right? There's going to be this polynomial has degree 4, so we've got some roots for this polynomial, and does the number 2 capture the upper bound of those roots? Meaning, are there no other root that is greater than 2? Okay, so we're going to test this upper bound of 2, and we're going to use synthetic division. So I'm going to grab these coefficients, 3, right, -5, 4, -10, and -4. I'm setting up my synthetic division, and I'm going to do my synthetic division. So the first step with synthetic division is to bring down the first number. So I write 3 here. 3 times 2 is 6, and then I add -5 plus 6 is 1. 1 times 2 is 2. 4 plus 2 is 6. Okay, 6 times 2 is 12. -10 plus 12 is 2. 2 times 2 is 4. And -4 plus 4 is 0. So that 0 at the end tells us the remainder. And so I got a blue sticky note here asking you, what does the 0 remainder say about the upper bound 2? Well, this remainder tells us that 2 is a root. So that's good to know. All right. Now we're going to use the upper bound test, and we're going to look at these numbers that we got, so these coefficients. And since all the coefficients are positive, we know that 2 is an upper bound of the zeros for p of x. So indeed, 2 is an upper bound, and it is a root as well, because the remainder is 0, and there is no greater root than 2. Okay, because we're saying it's an upper bound, so it's within this interval. Let's check the lower bound. The lower bound, because it's saying the interval is from -1 to 2, so the -1 is the lower bound. And we're going to do the same thing that we did before, but we're going to throw -1 over here in our synthetic division. So first step is we bring down the first number, 3. Okay, write it right there. 3 times -1 is -3. Add up, and you get -8. -8 times -1 is +8. 4 plus 8 is 12. 12 times -1 is -12. -10 plus -12 is -22. Negative 22 times negative 1 is positive 22, and then when I add that up, I get positive 18. So this negative 1 is not a root because the synthetic division did not give us a remainder of 0. But let's look at all the coefficients here, okay? So we go from positive to negative to positive to negative, okay? And since all the coefficients alternate from positive to negative, then this confirms that negative 1 is a lower bound of the zeros of p of x. So there is no zero or root of p of x that is smaller than negative 1. So we know that all the roots of p of x are going to fall in this interval, negative 1 to 2, okay? And we know that 2 is also a root. We don't know what the other roots are or how many there are in this interval. We're just testing the upper bound and lower bound. And just to review, when we're testing the upper bound, we want all the coefficients are positive, and then if we're testing the lower bound, we're going to alternate positive and negative, okay? So that's how we know that. All right, so now let's turn to page 98 in our book. And we did learn this in Algebra 2. It's the conjugate root theorems. And this applies to if we have a square root or if we have a complex number. So if I have a root that looks like this, okay, so an example would be maybe, like 2 plus 2 root 3, right? So A, B, and C are all just numbers, right? And we're going to call them A, B, and C because it just makes it a generic number. But they're not variables. These are just numbers, okay? So if the root is irrational like this, and we can have it in the form of A plus C root B, then we have a conjugate that is A minus C root B. So see how these are conjugates of each other? The A sign stays the same. A is the same. But the sign in front of the radical is what changes from positive to negative, okay? So that's how we get the conjugate. So if A plus C root B is a 0, then A minus C root B is also a 0, okay? We can also do the same thing with complex roots. If A plus BI is a 0, then its conjugate, which is A minus BI, is also a 0. Okay, so let's apply this conjugate root theorem. And it wants us to list, in orange, the problem is, list all the zeros of p of x. P of x is this polynomial of degree 4. And it's also going to tell us in the problem that negative I is a 0. So negative I is a complex root. So let's do this answer in green. If I is a 0, then its conjugate is negative I, and that is also a 0. So if I is a 0, so is negative I. All right, if I and negative I are zeros, then x minus I and x plus I are factors of p of x, okay? All right, so we know over here in this line, p of x equals x minus I times x plus I times some other polynomial that I don't know, but it's going to have a smaller degree than 4, right? All right, let's FOIL this, x minus I and x plus I. If we FOIL it, we're going to get this here, x squared minus ix plus ix minus I squared. This p of x and this q of x stay the same. And then when I FOIL it, I get this term here. But look what happens. I can cross out ix minus ix, right? Maybe I should make that thinner so you can see behind it. So I can cross out this and this. right? They can get crossed out. So what I'm left with is this x squared term minus I squared. What does I squared equal? Well, remember, by definition, I is the square root of -1. So then I squared is the square root of -1 squared, which is going to be -1. So we're going to write this x squared plus 1, because it's minus I squared is a minus a -1, so it becomes plus 1. All right? Okay, so hopefully you remember imaginary numbers from Algebra 2, because we are using them already. All right, so now let's solve for p of x. Sorry, not p of x, q of x. Let's solve for q of x. If I want to solve for q of x, I'm going to divide both sides by x squared plus 1. All right, so I get q of x equals p of x divided by x squared minus 1. Well, we can do that, right? Remember up above, our problem was in orange. I've got p of x right here, and I wrote it again down here. So we can see, remember what p of x is, okay? So let's do this division. Let's divide. I wrote p of x here again, okay? And let's divide it by x squared plus 1, just as it says over there. All right, let me get my pen. So the first thing we're going to do is say, all right, I've got x squared. What do I need to multiply x squared by to get x to the 4th? So x squared times x squared equals x to the 4th. All right, let's do that. X to the 4th, and then x squared times 1 is just going to be x squared. That goes here. Got to keep your terms underneath each other that are like terms, okay? So we're going to subtract, and when we subtract, it's got to distribute within this whole thing. So I'm going to minus it, okay? So my x to the 4ths cross out, bring down my 2x cubed, and then negative x squared minus x squared is minus 2x squared, and then I'm going to bring the rest down. All right, now we're going to repeat this process. I look at my term here, and I'm going to say, well, x squared times what is 2x to the cubed? So it's going to be 2x, because 2x times x squared is 2x cubed. I better write smaller because I'm going to run out of space. And then 2x times 1 is plus 2x. Okay, so I'm going to subtract that. Distribute my subtraction sign, it's really important. And I get negative 2x cubed. This crosses out, right? Because it's 2x minus 2x, so that's going to cross out. And I'm going to bring down my minus 2. Now I'm going to say x squared times what is negative 2x squared? It's just minus 2. So minus 2 times x squared is minus 2x squared. And then minus 2 times 1 is minus 2. And then if I subtract that, everything crosses out. And I've got a remainder of 0. Okay? Okay, so my answer for all this long division was x squared plus 2x minus 2. So I'm going to write that that's what we got for q of x, right? So q of x is x squared plus 2x minus 2. That's what we just solved for. So now let's set q of x equal to 0 and solve for x using the quadratic formula. All right, hopefully you have that memorized. So if we use the quadratic formula, let me just review this for you. The quadratic formula is, in this one, a is 1, right? B is 2, and C is negative 2. And the quadratic formula is opposite of B plus or minus the square root of b squared minus 4ac all over 2a. And this is what x equals when we solve this. Okay, so if I plug this in, I'm going to get negative 2, that's the opposite of b, plus or minus the square root of b squared, so 2 squared, minus 4ac all over 2a. And the reason why I say all over is because it includes this over here. We need to make it all over the 2a. All right, so then if I reduce what's in my radical, I'm going to get 12, so the square root of 12. Well, remember, 12 is 4 times 3. So if I take the square root of that, I get 2 root 3. Okay, you following along? And then I can factor out, if I look at this numerator, I can factor out a 2. Remember, the 2 in the denominator is all under the whole numerator, not just one of the terms. So we need to factor out that 2 in the top, and then we can cross out our 2's. Now we can cross out factors. So x is negative 1 plus or minus the square root of 3. All right? So the answer to this problem is, all right, let's remind ourselves what this problem was, because it was a lot of things. So it wanted us to apply the conjugate root theorem, right, and list all the zeros. It wants us to find all the roots of p of x if negative I is a 0. So by applying the conjugate root theorem, we're saying, well, if I is a 0, so is negative I. And then we can get our factors, x minus I and x plus I. Those are our factors. So we use that to divide p of x by that FOIL factor, and that gave us q of x. Okay, so once we got q of x, we were able to solve for the roots or the zeros of q of x, and that gave us all the zeros of p of x. So the final answer is x is plus or minus I, and negative 1 plus or minus the square root of 3. So remember, our imaginary and our irrational roots come in conjugates. So that's why you see 2 of them. So there's 4 roots in total. Okay. Let's go to the next problem. Let's see, where is it? Okay. So now we're going to apply Descartes' rule of signs. We're still going to work with that p of x that I had in orange up top. And we're just going to remind ourselves, we did this in class, Descartes' rule of signs. So if I look at p of x here, and I look at the sign changes of p of x. So I go from positive to positive, so that's not a sign change. But here from positive to negative, I've got a sign change. Then it goes back to positive, and then it goes to negative. So I've got 1, 2, 3 sign changes. So p of x has 3 sign changes. That means I have 3 or 1 positive real roots. Okay? Now we're going to look, Descartes' rule says next, to look at the negative real roots, let's look at p of negative x. So we're going to plug in negative x into p of x. And really what that's going to do is change the sign of every term in p of x that has an odd exponent. So x to the 4th is not going to change sign because it's an even exponent. So a negative times a negative is a positive. So when we have x to the 4th, it's going to stay x to the 4th. But now let's look at 2x cubed. Well, x cubed is an odd exponent. So our sign is going to change from positive to negative. So when we write p of negative x, our sign is changing. Now, negative x squared is going to remain negative x squared because that's an even exponent. 2 times x is going to change to negative 2x, all right, because that x is an odd exponent. 1, right, it's invisible, but it's there. And that means if we plug in a negative x for x, it's going to change the sign of that term. All right, so now we've got p of negative x, and we go from positive to negative, but then it's going to go negative again, negative again, negative again. So it didn't change once it turned negative. So we just have this one sign change right here from the first term to the second term going from positive to negative. So that means I'm going to have one, because there's one sign change, one negative real root. So this is using Descartes' rule of sign to look at our p of x from example 6. All right, let's also, for review, let's apply what we just learned, the upper and lower bound test, to confirm that there's no real zeros outside of the interval -3 to 1. All right, remember p of x was what we have here in orange. And the upper bound, if we look at our interval, the upper bound is this 1. So I'm going to put 1 in this box, okay? And I'm going to do my synthetic division. So I'll bring down my 1. 1 times 1 is 1. 2 plus 1 is 3. 3 times 1 is 3. -1 plus 3 is 2. 2 times 1 is 2. 2 plus 2 is 4. 4 times 1 is 4. And -2 plus 4 is 2. So if we look at all our coefficients there, we'll see that they are all positive coefficients. So yes, they're all positive, and that means that 1 is confirmed to be an upper bound of our roots. So there's no root of p of x that is greater than 1, okay? 1 is not a root because our remainder is 2. It would only be a root if our remainder was 0. So 1 is not a root, but there's no root that's bigger than 1. All right, let's look at our lower bound. In the question, it wants to know if -3 is a lower bound. So we're going to test -3 in our synthetic division to see if it's a lower bound. So we're going to first bring down that 1. 1 times -3 is -3. 2 minus 3 is -1. -1 times -3 is 3. -1 plus 3 is 2. 2 times -3 is -6. Hold on, did I do something wrong? Oh, no, that's right, okay. 2 plus -6 is -4. -4 times -3 is positive 12. -2 plus 12 is 10. Okay, so if I look at my coefficients here, I go from positive to negative to positive to negative to positive, right? So we're alternating plus and minus coefficients. The signs are alternating. So we are, and that means that it is a lower bound. So what was it, number, sorry. -3 is a lower bound of the zeros or the roots of p of x. So this is, there are no real zeros outside of this interval. Okay, so this is true. All right, let's move on. I'm turning to page 99 now in our textbook if you're following along. All right, we're still talking about p of x, that orange example 6 above. And we talked about the roots. We already gave the answer what the roots were. We said it was all that I have here in blue. So it was I plus or minus I. It was -1 plus or minus the square root of 3. So there are 4 roots. So if I have the roots, then I know the factors. So it's x minus I, x minus -I, which would be x plus I. Then it would be x minus -1 plus root 3, and then it would be x minus -1 minus root 3. Now I can easily, hopefully, reduce this and FOIL it to be x squared plus 1. And I can also multiply this, and we'll go into some detail later how to do that easier, to get x squared plus 2 minus 2. So this is called the irreducible quadratic factor, and it means when you combine factors that occur in conjugate pairs, just foiling like they have above here, this is called the irreducible quadratic factor. Okay. Not too important, but just giving you some terminology in case the book uses it later on. All right, let's move on to example 7. This is the last example for this section. And we want to write a polynomial function of least degree. So we don't want to have like x to the 10th power if we can avoid it. We want to have the least degree with integral coefficients. So that means that the coefficients are integers and has zeros of 0. So the roots are going to be 0 with multiplicity 3, 2/3, 1 plus square root of 2, and 3 minus 2i. Okay, this is not going to be a short problem, so stay with me. All right, so we're writing a polynomial. We're coming up with a polynomial, and all we know are the zeros. We only know the roots. And some of them look like they're the irrational or complex roots. So we're going to be looking at the conjugates for those. So let's first look at 0 because that looks like it's going to be the easiest one over here. So root 0 has multiplicity 3. So that means x minus 0 is going to be a factor. And that's going to be cubed because it has multiplicity 3. So x to the 3rd power is going to be one of our factors. So that's easiest. Let's look at the next one, 2/3. All right, so we've got a root that's 2/3. That means we're going to have a factor, x minus 2/3 is another factor. So we've got one factor that's associated with the root 0. We've got another factor that's associated with 2/3. But if you look here at x minus 2/3, this just, it's like nails on a chalkboard to math students. We just don't like fractions, right? So we are going to multiply it by a constant to eliminate the fraction. And the easiest one to do would be 3 because that would wipe out the denominator there and get rid of that fraction. So if we do that, we get this factor here, 3x minus 2. So we've got x cubed as one factor. We've got 3x minus 2 as the other factor. Okay. What did the problem say? Let's go back to the problem. All right, we took care of 0. We took care of 2/3. The next one is 1 plus square root of 2. So let's look at this. If 1 plus the square root of 2 is another factor, right? 1 plus the square root of 2 is another factor. It told us that. So then we know its conjugate is 1 minus square root of 2, and that's also going to be another root. So let's do x over here, x minus 1 plus root 2 and x minus 1 minus root 2 because those are both going to be zeros. They're both, the 1 plus root 2 and 1 minus root 2 are both going to be zeros because they're the conjugate pair, okay? So I'm going to show you, I mentioned it earlier, how to foil this. There's actually a trick. If we use the associative property, we can obtain a difference of squares. So instead of my parentheses being here and here, I'm going to use the associative property and move my parentheses over to the beginning of that factor. So it's going to be x minus 1 in parentheses and then x minus 1 again in parentheses. So what's in parentheses is going to match, all right? By doing that, I can see I've got x minus 1 plus root 2, x minus 1 minus root 2. So this is starting to look like a plus b times a minus b. Okay, this formula is the difference of squares formula. A squared, my pen is not writing how I want it to. A squared minus b squared. Okay, you see that? So we are going to apply this formula where a is x minus 1 in parentheses, in the yellow parentheses, and b is the square root of 2. okay? So if I do that, then a squared minus b squared this is a squared